Hi everyone and welcome to a new video. In this video, we'll understand two new things. One is called program derived addresses and the other one is cross program invocations. We're doing these together because the concept of program derived addresses makes sense only in context of CPIs. So we'll understand what both of these things are, and in the next video we'll actually write some code to understand these further and see how you can use them in a practical scenario. So before we proceed any further, let's understand how we usually work in Web 2 when you're creating a big application. Let's say you'll basically have a database where you'll store the information of a user. And as your application, let's say, gets very complex, let's say you're building an e-commerce application, you'll have multiple databases. Let's say a purchases database where you're storing all the purchases that a user made, an address database where you're storing their addresses, a refunds database where you're storing all the refunds that a user has asked for, and so on. So these set of databases keep on growing, and in each of these databases there are these rows, each row representing a certain atomic unit of either a refund or a specific user's details, and so on. So that's how you generally structure an application in the Web2 world. And you have like servers and microservices sitting in front of these databases that your end user interacts with, passing in some sort of a cookie to authenticate themselves. So now let's try to understand how you can create a similar scenario in Solana. So up until this point, we have discussed the concept of accounts, and any data, if you want to store on the blockchain, needs to be stored in different accounts. So let's say you have a program and the program has to basically persist data across invocations. What you can do is you can create an account that you want the program to interact with. You can set the owner of the account to be this program, and then this program will have access to update the data inside this account, and then you can just make calls to this program, and this program will update the data inside it based on the instruction that data that you've passed to the program. The reason the owner of this account needs to be this program is because Solana runtime ensures that if the data of an account is being modified, the program that's modifying it needs to be the owner of the account. So this is why we had this check in the contract that we did before, because we wanted to ensure that whenever someone passes in a program ID, before we actually update the data, we ensure that the owner of that account that someone is passing in is actually that program ID. So if you pass in an account to this program that does not, whose owner is not this program, you should just exit it right then and there. Because even if you don't have this if check, this instruction will fail, but you can basically return a better error message here to your end user if you do this check up front. So yeah, only if that's the case do you actually update the counter. Now let's try to see if your application gets a little more complex, what all problems you can run into. So in the case of an e-commerce application, you'll have a bunch of these accounts because in the last program we were just storing a counter, but now this is an actual application. You'll have to store user data, you'll have to store their orders, their refunds, the items that are available on your application. So there will be a lot of accounts for a specific user, and it will be very difficult for them to keep track of all of these accounts. Let's say up in the last contract we were actually storing the counter on the front end itself. Like the counter account was the user's responsibility to maintain, and the user would pass in the counter account anytime they were calling our program. But in an application like this, it will be very difficult for them to keep track of all of the accounts that are storing their data. So is there an easier way to do that? If we don't do that, if we don't use the easier way, which we'll just discuss, this user will have to store these accounts and also send these accounts whenever they're calling this program. So that's a problem that we want to solve. Also, as you'll see in the future, there are a lot of contracts already available on Solana. So people usually write these contracts, get them audited, and they're very well written, documented, and deployed. So it a lot of times makes sense for you to just reuse a lot of these programs. So let's say there's a token swap program that's available. You could either just copy paste the code from inside the contract and just paste it inside yours, but that's just an ugly way of doing it, right? Because that program is well audited, they'll be maintaining it in the future, and it has a very clean API to interact with it. So why not just reuse the program that's already present? And also, when you're building an application, it generally is a good idea to structure your programs into smaller units of sub programs, which can solve a use case for you, but might just be able to solve a use case for someone else as well. So you can have like a parent program that can further call all of these programs individually. And then if in the future you create a different program or some other developer wants to use this specific functionality, they can simply call your program rather than going into your single program, figuring out the logic for it and copying pasting it into theirs. So to facilitate this, Solana introduced this concept of CPIs, which stands for cross program invocation. I think the name is explanatory in itself, that it allows a program to call other programs. So it's similar to in the Web2 world, think of someone calling a service and then you making an API call to another service to to delegate some jobs to it. So think of it in a similar fashion where you can reuse the logic or programs that are already deployed by making a CPI to it. But there are a few problems that can happen, or like there are a few issues that you can run into when you're doing this. So let's try to see what those are. Let's say you pass in an account and you know that accounts have these property of that they can sign a transaction, and to sign a transaction you basically need the private key of the account that you're passing in. So let's say I am a user, I am interacting with this e-commerce contract, and I want to send in the data. I want to send in my whoopsie daisy. I want to send in this account to be modified, or just let the program know that this is me. And for the program to be able to justify that this is you, there are a few ways they can check that. The easiest way is to just ensure that you've signed this transaction, because this is a contract on the blockchain, so anyone can call this and anyone can pass in any accounts to it, but only you can sign it because only you possess the private key of it. So that's easy for you to do, but as we discussed before, it's very hard for you to maintain all of these accounts. So what if you just had to maintain a single account, which is basically the one that you have Solana in your cold storage wallet or something like that, and your program, what if it could figure out the individual accounts, the individual data accounts to send it to each of these subcontracts? I'll repeat that. So up until this point, we were expecting the user to pass in the data account to a program and sign that transaction to let the program know that it actually owns it. But if in the future we want to the user to just maintain a single account and then the program to be able to figure out various accounts from it, how can this program do that? And also, it's totally possible that the program that this parent program is CPIing into expects that the account that it's getting has actually signed the transaction. So you need to figure out individual accounts for each of these programs to call on, and two, you need to sign on behalf of them. And the only way to do that is that you store the private key either on the program here, which you can, but you shouldn't, because storing private keys on the blockchain is not the best idea. So your user doesn't have each one of these individual accounts. You want to derive those accounts somehow and pass them in, which you can do by writing some logic, but you can't really sign on behalf of them unless you actually know the private key of it. But you can't store the private key either on the blockchain or write some logic to figure out the private key on the blockchain, because it's completely open. So how do you solve this problem? So this is where PDAs get introduced. You should never store private keys on the chain. And a PDA, which we will introduce in the next slide, is basically an account which has some special properties. One of the special property being that a program can automatically sign on behalf of a PDA as long as the owning program of the PDA is the program that's trying to sign on behalf of it. So let's try to understand that here. A program derived address is slightly different from a normal address, which is like a normal public key, private key pair that you have. One, this PDA doesn't possess a private key. So there's actually no way for you to sign a transaction using the private key, because there is no private key of this account. That's one of the properties of a PDA. And the second property is that if the program ID associated with the PDA, so it's a program derived address, the program that you're deriving this address from has access to sign on behalf of this account. So if you create a PDA for this program, so the account of which, or the program ID for which is the program ID of this program, this account can then be signed by this program. So that's written inside the Solana runtime. Okay, before that, how can you create a PDA? So the easiest way to create a PDA is the PDA expects two inputs. One is the program ID that the address will be derived out of. And the second is a list of strings. These can be like random strings that you can send, but there's usually, it's left to the application developer to write these seeds in like a certain fashion for them to be able to derive the right addresses. But the idea is that the combination of these two, a program ID, a parent program ID, and a bunch of these seeds spits out a public key. And there is no private key for this account. And this account has a special property that this account has access to sign on behalf of this account. I'm using account too many times here, so I'll maybe rephrase that. This program has access to sign on behalf of this account. And we'll see how you can do that. But the basic idea is that as long as your program here is able to derive a few of these addresses, that program will have access to sign on behalf of these of those accounts, and only that program will have that access. So if you create a PDA here, you can sign all of these transactions, but let's say this guy is making a CPI ahead, this guy cannot sign transaction based on the PDA created here. This will have to create its own set of PDAs where the program ID is this program ID. So that's a property of a PDA. Let's try to see how that works in a bigger application like e-commerce application. So generally, this is how I would structure a Web3 e-commerce app. You basically need to be able to store a user's address, their profile, each of their orders, and their refunds, right? So whenever your user calls your parent contract here, they'll basically tell you, hey, I want to update my address, or like, hey, I want to initiate a new refund. And then this program needs to figure out where exactly, which program needs to call. So if it's a refund, it'll call the refund program most probably. And then it also needs to figure out what's the PDA for this specific refund. So that's where the seeds come into the picture. You'd generally devise seeds in this fashion. So let's take a step back here and see how you would create this application in the Web2 world. Let's say there's a user, the user ID of that user being user one. You'd most probably store their name and all of these details in like a profiles database, and the user ID as the primary key of their row. Similarly, their address in an address database with the primary key being the user ID. You'll store their order in like an orders database with the primary key of each order being the user ID and the order ID. And similarly, a refund being stored in the refunds database with the user ID being, with the primary keys being the user's ID and the refund. So the idea is that you can uniquely define a row using the user's user ID and their refund ID to get back that unique refund or the details of that unique refund. So you structure the seeds in a similar fashion. Your end user will simply call your contract and tell you, hey, I want to update this specific refund, or let's say I want to update my address. So they'll just tell you, I want to update my address, and you can figure out the PDA. Devise it in a way that let's say the first string, like you can devise it in multiple ways, but this is one of the implementations, which can be, okay, the first one will be the address and the second one will be the user's public key. If I create these two seeds, I can uniquely identify an address where I will store this user's address. I've used address 2 times. I can uniquely identify an account which stores this user's address. Similarly, if the user says, hey, I want to check the details of order number 1, what you can do is you can create a PDA or derive a PDA with these seeds, order being the first seed, user ID being the second one, and the order ID being the third one. Using these 3 and this program's ID, you can derive an address, and you can just embed logic in your program that I will always store a user's order in this fashion. So all their PDAs for their orders will be derived like this. So this gives you a way to derive addresses based on the instruction data that's coming in, and your end user no longer needs to maintain a list of addresses. Also, the other thing that we discussed was signing on behalf of a user. So whenever your user makes a call here, You will most probably have individual contracts for each one of these. Some of these, let's say you've written, some of these, let's say, are already written on the blockchain and you're reusing. These programs will expect you to sign the transaction that you're sending the account for. So let's go back. When your user tells you that they want to initiate a refund, your contract will call a subcontract that, let's say, stores the data inside, initiates the refund and puts the data inside an account. You need to CPI into that, and that contract will want you to sign that transaction. But since the account that you've created for this user, this PDA with this program ID and these set of seeds, since the program ID is this parent program, it can sign on behalf of it, and hence this program can actually call that other program, sign on behalf of this account, and ensure that the refund contract does what it's supposed to do. So yeah, your user will call this parent contract. You will figure out their PDA based on the instruction data. You'll figure out what they want to do, figure out the PDA for that specific set of data, call the right program for it, sign that transaction, and that's it. That will basically should be the general way to structure a big Web3 application. And PDAs and CPIs help you do that, and PDAs are the easy or the better way to actually arrive at something like this, with your end user just having simple logic to call your parent contract, and then you're figuring out things from there. So that's the gist of PDAs. It takes a few times to wrap your head around it. It took me definitely more than a few days to understand it, but once you get the gist of it, which you most probably will after you write a few contracts and like do a bunch of these CPIs, then it's very easy to understand why this is very intuitive, and it's also very difficult to go back to normal Web2 world programming, because you start thinking in an accounts model versus thinking in a database model. So let's write a contract in the next video. The contract will basically call two subcontracts, which we'll also write. The address subcontract updating a user's address, and the user subcontract updating a user's name, age, things like that. And the parent contract basically being the one that your user will interact with, send in the instruction data, expect your e-commerce contract to create the right set of PDAs and do the right set of CPIs for the individual instructions, and then we'll do some validations on the client to ensure that it's working as expected. So let's dive into that in the next video, and maybe that gives you a better sense of both of these concepts. So I'll see you there. Okay, so in this video, we'll be going through each of these contracts, one being the parent contract that a user interacts with, and an address contract and a user data contract. The purpose of these subcontracts are to take an account as an input, which could be in PDA, could not be a PDA. The point is that the input that's coming in needs to sign this transaction, and what the address program will do is it'll update the address of the user based on the incoming instruction data. Same thing for user data. It'll just update the data, things like name, date of birth, in the incoming account, as long as the incoming account has signed the transaction. So let's go over the address program first. This is an easier one. This is actually very similar to the counter contract that we did a few videos ago. So we derive two structs, the instruction data. The instruction data will expect an address, which is a string. A string can also be represented as an array of bytes. And in this case, we've restricted the size to be 512 bytes because probably no one will have an address longer than that. The reason for this is you can't really deserialize a string or an array of bytes which does not have a fixed length. So you need to specify the length here. A good thing to do here is to generally have the size as big as you expect the input to be, maybe a little bit more than that. The other thing that we're defining here is the address schema, which is basically the schema of the data that you'll shove inside the account that comes in as an input. And this is a helper function that takes a string as an input and returns a bunch of bytes as an output. This is actually not needed in our main contract. This is just used in the test, so feel free to ignore it. And coming to the actual contract, as you remember, the three inputs to a program are the program ID, the accounts that need to be touched in this contract, and the instruction data. So the instruction data looks something like this, which is basically an address. So the first thing we do is we extract the instruction and ensure that it's of it resides it's of this the form of this schema, which is this thing right here. Basically, it has an address field which is of 512 bytes. And if that's not the case, we return an error. We then iterate over the accounts that the user has passed in. And if you remember from the diagram here, the contract only expects one account as an input, which is the account that will store the data. So this is very similar to the counter account that was being passed in a few videos ago, where we were storing the actual counter. Here we are storing the address of a user. So what we do is we get the account, we store it in this variable. We ensure that the owner of this account is the program ID, because this program is actually trying to update the data inside this account. So it needs to be the owner. So whoever is passing in an account to this address contract needs to ensure that the owner of this address is actually this account itself, because if that's not the case, this account won't be able to update the data inside this incoming account. The other thing we're checking here is whether or not the account that's passed in has signed this transaction, and that needs to be the case, because if you don't do that, someone can pass someone else's account here and make the contract update the data inside it. If the incoming account has signed the transaction, you know that the person who owns this account or the contract who owns this account has signed this transaction. After we do these two checks, we simply put the address inside the address field of this account and serialize it back. And that's all this contract does. So very simple contract done and deployed on DevNet, and anyone can interact with it as long as the account that they're passing in has signed the transaction and the instruction data has the right schema. They'll be able to, and of course the owner is the program. This program will be able to update the data inside it, specifically set the address field to whatever you're passing in as the input. So we independently deploy this contract on DevNet, and I've already done that. So that took us through our first contract. Let's go to the second one. So the profile contract looks very similar. Only thing is that the input is actually a little different. You now take an input the date of birth of the user and the name of the user. So that's the only difference here. Everything else will be the same. And this is also independently deployed. Now coming to this central parent contract that your user interacts with. So this contract will expect three types of instruction data as an input. Either an instruction to update the address, update the user info, so basically CPI into this one or CPI into this one, or initialize the contract. So let's get into these one by one. So what happens is eventually when your contract will be deployed, this is an e-commerce application, right? So your user, whenever they come to your application, they'll sort of sign up using Phantom. When they do, their data will actually now be stored somewhere in these individual some accounts, and they can update their data, they can update their address. That's the functionality of this whole these three set of contracts. So when the very first time they come and sign up, they need to call this contract with initialize as the instruction data. So what this will tell our contract to do is it will basically tell our contract this is the first time that the user has come. So you should probably initialize a bunch of accounts for them for storing their address and storing their user. Again, this is a little different from how we did it in the last video. In the last video, we expected the user to create the account and pass that in for their counter. But now, in a more sophisticated scenario, we're wanting our users to only send us their own account, or like only maintain their own account, and everything else, their address, their refunds and everything, will be stored inside contracts which can be derived from inside this program. They don't need to worry about storing them somewhere. So the only input we ever receive from them is their account and what they want to do. And then we have somewhere derived and defined the various addresses where we've stored their data. So let's get into the initialize function. If you look over here inside our program, if the user passes an initialize as the instruction that they want to execute, what we do is we first extract all the accounts that they're sending. And here you'll see there are a bunch of accounts. Let's go over each one of these one by one. So what the user is doing now is they're telling you, hey, this is the first time I'm coming here. Please initialize a user account for me, a program account for me, because I'll be in the future storing my address somewhere and storing my user data somewhere. So please initialize do your thing, do whatever you need to do. So what this guy needs to do is, and we already know that whenever your program is interacting with a few accounts, we expect all of these accounts as an input. This is what makes Solana faster. So the user actually has to send a lot of data. The account, this thing is basically this user's account, the place, their phantom account, the place where they store their Solana, the normal wallet that they use to interact with the e-commerce application. The update user info account. This is the account, basically this thing right here. This is the account which will store not this one, this one. This is the account that will store their user data, their date of birth and their name. And as we'll see soon enough, this will actually be a program derived address. The contract, which basically represents the address of this contract right here. Similarly, the the address account represents this account right here. The user profile contract represents this contract, and the update address contract represents this contract. So we have these four things that the users passed, and they've passed in the system program as well, because you'll be interacting with the system program here as well. So they need to pass that in as an input. Once we have all these accounts, we do a bunch of validations. So here comes a very important thing. Here's where we'll define PDAs. So there's a function I've written that says get address seeds. I should probably name this better. It should probably be called get address PDA. So what happens is that here you want to initialize this address PDA for this user, because in the future they'll be calling your an update address instruction. So you need to make sure that the accounts have already been initialized and they have the right set of Solana inside them so that they can exist on the blockchain, because they'll be storing some data. You do all of that in this initialize method. So the first thing we do is we find the program derived address. So that's what the get address PDA function here does. If you look inside, what we're doing here is we're calling find program address. This is a function exposed by Solana. We're passing in a few seeds. Now, if you remember from a few videos ago, the place where we'll be storing the user's address, the seeds should look something like this: the string address and the user's public key. And if you look here, that's exactly what we're passing in here. We're trying to find the final address that will be derived out of this. So if we go back a few slides, this address right here that can be derived using the program ID, the current parent program ID, and these two seeds, address, the string address and the user's public key. That's what this function will return you. So find program address is a Solana exposed function which based on the seeds that you've passed in returns you a public key, which public key can actually be signed by this program, because that's a public key derived from this account, from this program. If you look closer here, when we do the call actually returns you two things. It returns you the address account, the found address account, which is basically this account right here. It also returns you something called as a bump. This is a small concept we haven't discussed up until this point. The basic idea is, that a PDA, we defined one property of a PDA. It cannot have a private key that ensures that no one else other than the program that owns it can sign it. So if a PDA cannot have a private key, it might just happen when you're calling. So whatever is the algorithm to derive the final PDA out of these seeds and this program ID might just have a private key. So what this find program address does is it adds a new seed to the end of it. And if you go through this text, you'll understand this a little bit better. When you pass in a bunch of seeds, what find program address does is it adds a new seed to the end of it, which is just a single byte. So anything from 1 to 255. And it iterates on all of these from 255 to 54 to 53 like that until it finds an address which does not have a private key. So what might happen is when you're passing in these strings, right, Let's say there's an algorithm to derive that program, the public key that will be returned with these seeds and this program ID. If the first public key that comes just from these seeds has a private key associated with it, that means you can't use it as a PDA. So what Solana does is it adds a new seed. These are the two seeds that you've sent. It adds a new seed to the end of it, which is called a bump. This is just a single byte. It iterates the byte from 255, goes down to 0, and as soon as it finds a public key which does not have a associated private key, it returns that. So you will always get two things from it. You'll get the found address, the address that it found, and a bump. And you need to make sure that whenever the find program address function that you called does this. It receives a bunch of inputs and ensures that it returns a bump as well. And the combination of these inputs and the bump, when passed into the public key create program address function, will return the same public key. Okay, things got a little confusing here, so let's try to see the difference between these two functions, find program address and create program address. So they basically look the same. They expect the same set of inputs, but what the first one does is it also finds a bump that when added to the end of it, so let's say it returned a bump called which looks something like this, just 1. When you're calling create program address, you need to pass in the address, the set of seeds that you passed in above, and one more thing, which is the bump. So these seeds actually derive your PDA. You might think what derives your PDA is just these two strings that you wanted it to derive, but Solana needs to make sure, we need to make sure that we have another seed here, which is the bump. And the reason for this is that if you leave the set of seeds to just the user who's defining the PDA, it might just happen that the seeds that they're passing in don't have an associated does have an associated private key. So we always need to have a bump to the end of it, and this bump is decided by Solana. And the way they decide it doesn't matter. The basic point being, the seeds that you send in are sometimes just not enough to create the PDA, so it will always return you this bump, and we'll see why we need this bump later on. But for now, that's all we need to know, is that when you want a account to be derived out of a bunch of seeds, it will return the final derived account and it will return a bump, and we'll see why we use the bump later on. So this function returns you the PDA that you want to initialize for the user, where you want to store the user's address. We do a small validation here to ensure that the found address that we've just found here matches the address that the user passed in as an input. So I just print the found address here to the screen. Then I do the same thing for the user account. I initialize the user account by calling get user profile seeds, which is a function that looks very similar to get address PDA. Only here the seeds are the word profile and the user's public key. And similarly, we get back a bump and a found user account, and we do the same validation here for the other account. Now comes the important bit of actually initializing this PDA and this PDA, which means actually putting some Solana inside it, because in the future we'll want to store data inside it. So the way you do that is you just call create account from the system instruction library, and the inputs that it expects is the account that's going to pay for it. We're going to make the final user pay for it. The new account's public key, which is the thing that we've derived here, both for address and for profile. The amount of Solana you want to put inside it, which is just enough to rent exempt for storing the address schema amount of data. The amount of data you want to store in it, which is basically just enough to store what the address schema looks like, which is something like this. And finally, who is the owner of this PDA? So as you know here, this address in this contract that we defined earlier, the address contract, we checked that the owner of the account that's being passed in needs to be this address contract. So we need to make the owner of the each of these PDAs to be, for this one it needs to be this account, for this one it needs to be this account, because these accounts are the ones that actually have access to update the data inside these PDAs. This one does not. This one just delegates these accounts and is the address from which these two are derived, but it's not the address which the PDA's owner is not this account. The PDA is derived out of this program. So this program has authority to sign on behalf of this PDA, but this program is not the owner of this PDA. The owner is actually this address contract. And the reason for that is the address contract needs to update the data inside this PDA. We call this we call this instruction. We pass in the accounts that this instruction needs. So this is actually a different contract that's deployed and it's maintained by Solana. Since this guy needs to pay for the transaction, it needs to be passed in as one of the accounts. The update address account needs to be created, so it also needs to be passed. And since the system program is what might be used inside this as well, so that's you need to pass that as well. These are the set of accounts that we're sending in, and the account already signed the parent transaction. So whenever your user is calling your e-commerce contract, they'll sign this transaction, and hence that signature can be propagated to this system instruction as well. They do need to sign this because they're the one who are paying for this newly created PDA. But the other person who needs to sign is the account that's being created. So whenever you're creating an account, the account that's being created actually needs to sign that transaction, which in this case is the update address account. Now, as we discussed earlier, update address account is actually a PDA. So since the update address account is a PDA, it can't sign a transaction because it doesn't have a private key unless the transaction is being invoked by its parent program, which basically means the program that this PDA is derived out of, which in this case is the case. This PDA is the program ID that we passed when we were creating this PDA was the program ID of this parent contract, and hence it can sign this transaction. And the way to do that is when you're signing, when you're creating, calling invoked underscore signed, you pass in as an argument the set of seeds, which when combined with this parent account, parent program ID, result in this update address account PDA. I'll repeat that. If you want update address account to sign this transaction, since this is the first argument here, which is this whole thing, which it basically is the set of seeds that when combined with this program that's CPIing, which is basically doing the CPI, which is the parent e-commerce contract. These seeds, when combined with that program ID, if they result in this update address account, the Solana runtime will assume this contract to be signed by the update address account. So that's the power of PDAs basically. You derived this PDA here, and since this PDA was derived out of this parent program, it was able to sign this transaction. And in the address account, since we're doing that validation will pass, and the address account will in the future be able to update the data inside this PDA. So we do the same thing for profile, the other one, which is this thing right here. We initialize this PDA and the instructions are the same, only the owner now is a little different. The owner is this program. That's all the initialize function does. Let's quickly look at the update address function and then go into the client side code and see how this all pieces together. So whenever the user passes in the instruction data such that the instruction type is update address, they'll also pass in an address. You can see that here. And the address is again a byte string of 512 bytes. If I look at the update address, what it needs to now do is your user is calling your parent contract and telling, hey, I need to update my address. So basically you need to find the PDA where you're storing their address, and you need to call this contract, the update address contract, and pass in the PDA and sign this transaction. And that's enough for you to execute this thing that the user wants you to. So let's see how you do that. You first extract the accounts that the user is sending in. In this case, the user needs to send their own account, the update address account, which is this PDA, and the update address contract, which is this contract right here. That's all the inputs that you need. We renamed this function, so let's do that here as well. We get the PDA for this user, and we basically do the same validation here, where we ensure that the found address account is same as the one that the user passed in, by just checking that if the account that's derived from this user's account and the address string is the same or not. Next thing we do is we call invoked underscore signed here, and let's look at each of these inputs that we're sending in one by one. The first thing is the instruction. Now, the instruction that we're calling here is this thing right here. We're basically calling this program, right? So we need to pass in the program ID here, which is the update address contract dot key. Accounts that we want to send in. So what does this contract expect as an input? It just expects the PDA, and that's what we've pushed here. It's the update address accounts key, and this is a signer and this is a writable account because we want this to write to it, and this contract expects this to be signed. And the set of accounts that you need to pass in is just the update address account, which is this PDA. If you remember, that's the, if I go to the address contract, that's the address that we extract over here. So just a single address that's been extracted, and that's what we pass here. And finally, since this needs to be signed by this PDA, as we remember from the discussion a few minutes ago, it can be done as long as this PDA is derived from this program, which it is, and we pass in the right set of seeds here, the seeds being address, this user's account, and the bump. So this is where we actually use the bump. I actually missed that here. We'll be doing that when we sign the transactions, when we're initializing as well. The bump needs to be passed in here as a seed. So the program is actually derived from these two seeds that you initially wanted it to, and the bump. So you need to pass all three of these here, and that is enough for you to sign this transaction. And since you've signed this transaction, and since you know this account is actually owned by the e-commerce, the address contract, the address contract will just execute as expected and update the user's address. So that's a lot of information, and that's a lot of Rust code as well. So let's actually go to our client and see how the client interacts with it. I've already deployed all three contracts on DevNet. So that's what our client will be interacting with. Let me change my editor and let's go inside the client. There are a few files here. The important one is, this is the top level file. So what we'll be doing is all three of these are just creating a connection. Let's forget them for now. We're calling initialize on the contract. We're calling update address, and then we're confirming that the address that we got for this user is the one that we passed in here. So let's look at all of these functions one by one, but that's the general flow of the function that we'll be calling. So these are defined in this index.ts file. It's a pretty big file. So let's go from the top. This is a random, very big account data that I've put here, because the parent contract, which is basically this user's account, needs to have some Solana. So we'll use this later on to just airdrop some Solana to this user. These are the three contract IDs for, this is the parent contract, this is the address contract, and this is the profile contract. I'm just hard coding them as strings here. A bunch of variables that will be defined and used later on. The address schema that actually, as you remember, is like a struct which has one field, which is the address, which is by an array of size 512 bytes, and a function that takes a string as an input and returns a set of bytes as an output. We'll see where we use this later on. Establish connection is the first function that we call. It basically creates a connection to local at DevNet, whichever one you define. In our case, in our config, it's defined as DevNet, so that's what it will connect to. Establish player. So this is a function that will start to fill a bunch of these local variables. The pair being the parent account or this person right here. So we initialize the pair by just checking my Solana config and getting the key pair from here and initializing it. We also airdrop some Solana to it. Yeah, that's pretty much what we do here. The check program function checks whether or not a parent program account actually exists. That's what we do here. And it also initializes an address program ID and a user profile program ID. These are the PDAs. Now you might think, why are we defining these here? As you remember, like even if you're calling the initialize function here inside the parent contract, you actually need to pass the PDAs that haven't yet been created. Like the purpose of the initialize function is to initialize the PDAs for storing the user's address, but they need to be passed in as an input. So when you're on the client side trying to call the contract, you actually need to pass these in as an input, and hence we're just caching them here by calling the find program address function, passing in address as the first string and the user's public key as the second seed. This find program address is similar to the find program address here. Both of these actually iterate over a bunch of bumps and find the right bump and return you the address with the bump. So this might actually just return two arguments. The public key and the bump, and we're just storing the public key here because that's the only thing that we need. Moving on, now comes the important part, us calling the initialize function inside the contract. So that's the next thing we do inside main.ts. Initialize, all it needs to do is first it needs to create the instruction data, which is this thing right here. Now, since instruction data is actually an enum, we discussed this in the last video, but the way to create an enum and convert it into bytes, one of the ways is that the first byte that you're sending in represents the index of the enum. In our case, we want to call initialize it at index 0, 1, 2. So that's what we're doing here. 2 here represents that the type of the enum is initialize, and since initialize doesn't have any data, this doesn't look very complicated. Later on, we'll see when we want to pass in data what this looks like. So that's what we've defined here. The data is actually the third argument, which is the instruction data. The keys represent all the accounts that are needed to be passed in, basically the accounts that we extract here, parent account, PDAs, contracts, and so on, and system account in the end. And finally, the program ID. This program ID is the parent program ID, which is this thing right here, the program ID of this. And we simply send and confirm this transaction. That's all we do. We are also signing this transaction from the pair's public key, because the pair needs to pay some money to create the PDAs. None of else, as you can see, are signing the transaction. Once this is done, hopefully it works and it creates the PDAs for both the users. The next function we call inside main.ts is update address, which expects the address string as an input, and it makes the user, it calls the parent contract only, but the instruction data that's now being passed has index 0, and it's also passing in the address string to the instruction data. Index 0 represents, if I go to instruction data here, basically the first one, and the address is a 512 byte array, and that's what we're initializing here and putting that in the instruction data. Finally, we're calling our parent program ID, passing in the data and sending the right set of accounts, the pair, the addresses, the PDA for the address for this user, and then the address contract, which is this thing right here. That's what your lib.rs expects when you're updating the address, these 3 accounts. And we execute this transaction. Finally, we call the get address function, which will, all that it'll do is it won't interact with any one of our contracts. It'll just go to the PDA and like get the data inside it and see if the address stored there is the one that we try to store when we updated address. So we just get the account info for this address program ID, which is this PDA. And once we get that, we try to deserialize it and just log the address here. It should hopefully be the address that we've passed in here. So that's the general flow. Let's try to run this file. So as you can see, the thing that's logged in the end is 2265 Mohali, India, which is what I passed here. Here. Now let's try to do the same thing again. Let's update my address to, I don't know, 1, 2, 3, 4. One important thing to note here is we no longer need to call initialize because we've already initialized the PDAs. And if we actually call initialize, it will fail with an error. The error will look something like you're trying to initialize an account that already exists. So we don't need to do that. The reason for this is that the public key, the parent account is still being fetched from my Solana config. So it's the same thing that was passed the last time that I called it. So I don't need to initialize the PDAs anymore. I just need to call update address and ensure that it gets updated. So let's run this again. And as you can see, the address has been updated. So if you want to, let's try to explore all of these accounts on the Solana Explorer now. So let's just log both the PDAs. Where can we log them? Right here. Address PDA. And user profile PDA. Let's run this one more time. Again, it's using my account from my Solana config, so it will be the same address PDA and the same user profile PDA. There you go. Let's copy the data for the address PDA and let's see what it looks like on DevNet, because that's where I've deployed the contract. As you can see, this is an account. It has some balance. It also has a size of 512 bytes as expected. The assigned program ID, what do you think this should be? It should be this address program here. If I go here, yeah, what does this look like? 3F, right? And if I look at the constants, 3F is actually the address contract ID. So everything looks same. And if you're fetching the data and trying to deserialize it, we see that the data is stored inside is the one that we sent in when we were updating the contract. So things now work as expected. I'll push all the code on GitHub. As an exercise, try to add two more functions here, update profile and then get profile. So just call the other contract here and see how that works, what issues you run into. Like one issue I can see that you might run into is it might be difficult for you to understand how or like create this instruction data, because you need to convert it into binary and the input expected is an enum. So like this thing is easy to do, but this might be a little tricky. You need to pass in a few things as an input when you're calling the other one, the profile contract. You actually need to pass in the name, the date, month and the year. So this might be tricky, but other than that it should be fairly straightforward. So try to do that. I'll leave that as an exercise. And yeah, by the end of it, what we've done is we've understood two concepts now. One of them is CPIs, so programs calling other programs, and the other one is PDAs, and they usually go hand in hand. A lot of times contracts are defined to expect something as input which needs to sign the transaction, but a lot of times you don't want your end user to maintain all the accounts where the data is stored. So PDAs give you a good gateway to do all of this. Your user can just call your contract and you can then derive various addresses for them and try to find pass the right set of contracts to various right set of addresses to various contracts you want to CPI into. That's it for this video. I hope some of this made sense. It took me a long time to understand this whole concept of addresses, storing data inside addresses and then PDAs. But once you start thinking around like this and thinking about structuring your applications in this architecture, it might make more sense, and it will be very difficult to go back to like standard Web 2 ways of storing data. So yeah, pros and cons. But I heavily encourage you to just code this on your own. And if there are any questions, post them in the comments. I'll try to answer as many as possible. And yeah, I think that marks the end of the Solana dev series, at least a beginner dev series. I think we've covered all the concepts. Next set of videos might include a framework called Anchor, which makes all of this much easier. Not sure if I'm looking at yeah, this is the right thing. So as you saw, it was very difficult for us to write these contracts, like extracting the accounts and doing a bunch of validations. And like it's also very counterintuitive to write code like this. And Anchor makes all of this a lot easier. So we'll try to look at that in the next series. So that's it. And yeah, hope you had fun. Oh, well, there's one more slide at the end. Try to go through what is being said here. It might make sense sometimes after you've coded a few programs, but this is a very nice explanation of program accounts and the create program accounts function and what bumps are, what seeds are, things like that. So I'll leave it at that, and I hope to see you in the next one.